299,792 kilometers per second. That is the speed of light. It is a speed so fast that a single photon can orbit our entire planet more than 7 times in the blink of an eye. To our limited human minds, this is instantaneous. When you turn on a flashlight, the beam seems to strike the wall immediately. When we look at the moon, we see it as it was a mere 1.3 seconds ago. This cosmic speed limit is the absolute fastest any piece of information or matter can travel through the fabric of space and time. Absolutely nothing in physics can ever outrun it. Yet, when we lift our eyes beyond our planetary backyard and look into the deep cosmos, this extraordinary speed begins to feel agonizingly, impossibly slow. In the grand arena of the universe, light does not zip across the cosmos, it crawls. It creeps across vast abysses of nothingness, taking years, centuries and eons, just across the gaps between lonely islands of stars. If you were to launch a beam of light from Earth toward the nearest star system, it would not arrive this afternoon, or next week, or even next year. It would travel through a freezing, silent void for more than 4 long years before it finally touched those incredibly distant worlds. We are trapped in a reality so colossally massive that our fastest cosmic messenger is reduced to a snail's pace. The distances are so great that we had to invent a new unit of measurement just to describe them without our math breaking down. We call it the light year, a metric that will completely shatter how you view your place in this vast, ancient, mysterious, and truly endless cosmos. Today, we are going to explore the light year and the cosmic gaps that defy human comprehension. If you are ready for this journey, please like this video and subscribe to our channel. Also, leave a comment below letting us know where and when you are watching this broadcast. To understand why the universe is governed by a speed limit that shatters our everyday intuition, we must first look at the very nature of light itself. For centuries, brilliant minds clashed over a fundamental question that seemed almost impossible to solve. Is light a continuous wave, like ripples spreading across a pond? Or is it made of tiny discrete particles, like grains of sand thrown through the air? The answer, as 20th century physics eventually revealed, is both. This bizarre reality is what physicists call wave-particle duality. Light exists as waves of electromagnetic energy, but it is also composed of tiny, indivisible packets of energy called photons. A photon is the fundamental quantum of electromagnetic radiation. It is the basic unit of light, and it is a truly unique entity in the universe. Unlike the atoms that make up your body, a laptop, or a distant star, a photon possesses absolutely zero rest mass. It carries energy, and it carries momentum, but it has no physical weight. This lack of mass is the exact reason why a photon can travel at the ultimate speed limit of the cosmos. In the framework of classical physics, if you push an object, it accelerates. If you keep pushing it, it should theoretically keep getting faster without limit. But our universe does not operate on classical rules when things begin to move extremely fast. Instead, it is governed by the laws of special relativity, which Albert Einstein formulated in the early 20th century. To grasp why the speed of light is an absolute unbreakable barrier, we must look at the profound relationship between mass, energy, and velocity. The famous equation, which states that energy equals mass times the speed of light squared, tells us that mass and energy are essentially 2 sides of the same coin. When you apply energy to an object with mass to make it go faster, you increase its kinetic energy. However, as an object moves faster and faster, approaching the speed of light, that added kinetic energy begins to behave as if it is increasing the inertial mass of the object. The faster the object goes, the heavier and more resistant to acceleration it becomes. If you wanted to accelerate an object with even a tiny amount of mass, like a single electron, to the exact speed of light, you would run into a catastrophic mathematical and physical wall. As the velocity of that electron approaches 99% of the speed of light, its effective mass swells dramatically. At 99.999%, the mass becomes colossal. To push it that tiny fraction of a percentage point closer to the cosmic limit requires an exponentially greater amount of energy. To reach the actual speed of light, the mass of the electron would become infinite, meaning you would need an infinite amount of energy to accelerate it any further. Because there is not an infinite amount of energy in the entire universe, it is physically impossible for any object with mass to ever reach or exceed the speed of light. Photons, however, bypass this limitation entirely because they are completely massless. They do not need to accelerate from a standstill. The very instant a photon is created, whether it is emitted by a burning candle or a massive star billions of light years away, it is already travelling at the speed of light. It cannot travel slower, and it cannot travel faster. It is locked into this single, eternal speed. This speed, which is exactly 299,792 kilometers per second in a vacuum, is not just a random number that happens to apply to light. It is a fundamental property of the fabric of space-time itself. In physics, this limit is often designated by the letter c, standing for celeritas, the Latin word for swiftness. This speed is the velocity of propagation of all massless particles and associated physical fields, including gravitational waves. It represents the speed of causality. Causality is the principle that cause must always precede effect. If information could travel faster than the speed of light, it would violate this principle, leading to mind-bending paradoxes where an effect could happen before its cause. For example, imagine a hypothetical device that could send a message faster than light. Because of the way space and time are linked in relativity, observers moving at different relative speeds experience time differently. To a certain observer moving at a high speed, a faster-than-light signal would actually appear to travel backward in time. You could receive a reply to a message before you even decided to send it. This would tear apart the logical consistency of our universe. Therefore, the speed limit is not just a barrier for physical travel. It is a vital guardrail that keeps the sequence of events in our universe running in a logical, orderly fashion. Before humanity understood this, scientists spent centuries trying to determine whether light travelled instantaneously or if it took time to cross a distance. The ancient Greeks argued about this, with some believing light was an instantaneous emission from the eye, while others suspected it must take time to travel. It was not until the late 17th century that a Danish astronomer named Ole Romer made the first successful measurement of the speed of light. Romer was observing the moons of Jupiter, specifically the moon Io. He noticed that the predicted times of Io's eclipses changed depending on whether Earth was moving toward Jupiter or away from it. When Earth was closer to Jupiter, the eclipses happened earlier than expected. When Earth was farther away, they happened later. Romer realized this discrepancy was not due to some strange orbital behavior of Io. Instead, it was because the light carrying the image of the eclipse had to travel a greater distance through space to reach Earth when the two planets were far apart. By calculating the difference in distance and the delay in time, Romer proved that light travels at a finite speed, and he came remarkably close to estimating its actual value. Later, in the 19th century, the Scottish physicist James Clerk Maxwell unified electricity and magnetism into a single, cohesive theory of electromagnetism. Maxwell wrote down a set of elegant mathematical equations that described how electric and magnetic fields interact. When he calculated the speed at which an electromagnetic wave would propagate through space, the equations spit out a specific constant value. That value was exactly the speed of light. This was one of the greatest eureka moments in scientific history. Maxwell realized that light itself is not some independent, mysterious substance. It is an electromagnetic wave, a ripple traveling through the electromagnetic field. This discovery set the stage for Einstein. If the speed of light is a built-in feature of electromagnetism, then it must be the same for all observers, regardless of how fast they are moving relative to the source of the light. This simple idea, combined with the principle of relativity, led to the mind-expanding realization that space and time are not fixed, rigid backdrops. Instead, they are dynamic and relative. If the speed of light must remain constant for everyone, then space and time themselves must bend, stretch, and dilate to make it so. Thus, when we talk about the speed of light, we are not just talking about how fast a photon zips through a glass tube or across a vacuum. We are talking about the speed of reality. It is the maximum rate at which any change in the universe can influence another part of the universe. If the sun were to suddenly vanish this very second, Earth would not instantly fly off into the dark, cold void. Gravity, like light, travels at this cosmic speed limit. For 8 minutes and 20 seconds, Earth would continue to orbit an empty point in space, bathed in the light of a star that no longer exists. Only when the final photons and the gravitational wave of the sun's disappearance reached us would we feel the gravity fail and see the sky go completely black. This physical boundary shapes everything we see and understand about the cosmos. The universe has built an absolute wall that prevents us from ever exploring it in real time. We are forever separated from the present state of the stars, locked into a delayed view of existence. Understanding this quantum reality of light is our first step into a larger cosmic journey, a journey that forces us to measure the vastness of space, not in miles or kilometers, but in the time it takes for these massless quantum messengers to carry information across the dark, silent void. When we hear the phrase light year, our brains often make a common subconscious mistake. Because it ends with the word year, we naturally tend to categorize it as a unit of time. But a light year is not a measure of time at all. It is a unit of absolute staggering distance. It is defined as the distance that a single photon of light travels through a perfect vacuum in 1 Julian year, which is exactly 365.25 days. To understand the sheer magnitude of this metric, we must break it down mathematically. We begin with the fundamental formula from physics. Distance equals velocity multiplied by time. Our velocity is the absolute speed limit of the universe, which is approximately 299,792 kilometers per second. This is equivalent to roughly 186,282 miles per second. To find out how far light travels in a single year, we must calculate the total number of seconds in that year. We start with 60 seconds in a minute, multiplied by 60 minutes in an hour, which gives us 3,600 seconds in an hour. We then multiply this by 24 hours in a day, resulting in 86,400 seconds in a single day. Finally, we multiply this daily total by the 365.25 days of a Julian year. This calculation reveals that a single year contains exactly 31,557,600 seconds. Now, we multiply these two astronomical numbers together. 31,557,600 seconds multiplied by 299,792 kilometers per second. The result of this simple multiplication is a number that is incredibly difficult for our minds to fully grasp. It is exactly 9,460,730,472,580 kilometers. In miles, this distance is approximately 5,878,625,370,000 miles. 9.46 trillion kilometers. This is a single light year. To write this number out in its full form requires 13 digits. If you were to try and drive this distance in a car at a constant speed of 100 kilometers per hour, without ever stopping for fuel, food, or sleep, it would take you more than 10,800,000 years to complete the trip. If you were to board a commercial jet airliner travelling at 900 kilometers per hour, the flight would last more than 1,200,000 years. Even our fastest spacecraft, travelling at tens of thousands of kilometers per hour, would take tens of thousands of years to cross just one of these units of distance. But why does this number feel so completely unreal to us? Why does hearing 9.46 trillion kilometers produce a sense of blank confusion rather than a vivid, clear mental image? The answer lies deep within the biology of the human brain and the history of our evolutionary development. From a neurological and evolutionary perspective, the human brain was never designed to comprehend the scale of the cosmos. For millions of years, our ancestors survived in environments where only immediate, local distances mattered. Evolution shaped our sensory organs and our cognitive processing units to deal with a very specific, microscopic scale of reality. We evolved to estimate the distance of a running animal across a savanna, which might be a few hundred meters. We evolved to judge the height of a fruit tree or the distance to a nearby river, which might be a few kilometers. The maximum physical boundary of our evolutionary ancestors was defined by how far a human could walk in a single day. Anything beyond that horizon was practically irrelevant to survival. Because of this, our neural pathways are highly optimized for what scientists call local-scale visualization. We can easily visualize a distance of 10 meters because it is roughly the length of a large room. We can still somewhat visualize a distance of 10 kilometers because it represents a distance we can walk in about 2 hours. But when we push past these earthly boundaries, our spatial visualization systems begin to break down rapidly. When the human brain is presented with numbers in the millions, billions, or trillions, it experiences a cognitive phenomenon known as the number magnitude effect. Our brains did not evolve with the native hardware to construct accurate mental models of such extreme quantities. Instead, the brain treats these numbers using symbolic representation rather than direct spatial mapping. When you think of 1 trillion, your brain does not actually visualize 1 trillion individual items. Instead, it processes the concept as an abstract symbol representing an extremely large quantity. Neurologists studying how the brain processes numbers have found that we use a logarithmic scale rather than a linear one when estimating large values. To an untrained human mind, the psychological distance between 1 million and 1 billion feels roughly similar to the distance between 1,000 and 10,000. But mathematically, 1 billion is 1,000 times larger than 1 million. To put this scale difference into perspective using time, 1 million seconds is about 11.5 days, while 1 billion seconds is over 31 years. 1 trillion seconds is more than 31,000 years. This dramatic difference is mathematically precise, but psychologically, our minds flatten these vast intervals into a generic category of unfathomable bigness. This neurological limitation is called cognitive myopia. Our brains are spatially nearsighted. When we attempt to stretch our spatial reasoning to encompass a light year, the brain tries to use the same neural mechanisms it uses to measure a walk across a field. It fails completely. We try to scale up our familiar units of meters and kilometers, but the numbers quickly become so large that they lose all physical meaning. They become mere mathematical abstractions, black and white ink on a page rather than a true three-dimensional concept of space. Furthermore, our lack of direct sensory experience with these scales compounds our mental block. Every concept we truly understand is rooted in physical interaction. We know what a heavy weight feels like because we have lifted objects. We know what a hot day feels like because we have felt the sun on our skin. But no human has ever experienced a trillion of anything, let alone a trillion kilometers of empty space. We have no physical reference points. There are no landmarks in a vacuum. There is no friction, no wind, and no resistance to give us a sense of movement or scale. When we look up at the night sky, our eyes also deceive us. The human visual system is designed to perceive depth using stereoscopic vision, which relies on the slightly different angles from which our left and right eyes view an object. This depth perception only works for objects within a few dozen meters. For anything farther away, our brains rely on other clues, such as relative size, atmospheric haze, and perspective. But when we look at the stars, all of these visual cues disappear. The stars appear to us as flat points of light, pinned to a two-dimensional dome. Our eyes cannot perceive that one star is 4 light years away, while another star directly next to it is 400 light years away. To our visual cortex, they look identical. This lack of natural depth perception makes the night sky look deceptively compact, masking the terrifying, silent abysses of empty space that separate those points of light. To bridge this profound neurological gap, astronomers and educators often attempt to use visual analogies. They might tell you that if the Earth were shrunk to the size of a tiny grain of sand, the Sun would be the size of a billiard ball located a few meters away, and the nearest star system, Alpha Centauri, would be another billiard ball placed thousands of kilometers away on the other side of the planet. These analogies are helpful, but they still require us to imagine distances that are far beyond our everyday experience. They only highlight the frustration of our cognitive limits. This is the ultimate paradox of the light year. It is a unit of measurement created by human mathematics to describe a universe that human biology is fundamentally incapable of visualizing. We have used our advanced analytical tools to calculate the exact distance a photon can travel in 31 million seconds. We can write down the 13-digit numbers, and we can use them to calculate the orbits of distant galaxies with absolute, flawless precision. Yet, when we close our eyes and try to feel that distance, to truly understand the vast, cold emptiness of a single light year, we find ourselves standing at the edge of a cognitive cliff. Our evolutionary heritage keeps us anchored to the soil of Earth, unable to truly comprehend the scale of the cosmic ocean we are floating in. The light year remains a beautiful, terrifying monument to the limits of our minds, a distance that breaks our brains and forces us to accept that the universe is far greater than the small, local world we evolved to understand. To begin our physical journey across the cosmic scale, we must first step out of our terrestrial environment and explore our immediate cosmic neighborhood. On this scale, measuring distances in full light years is impractical because everything is far too close. Instead, we must slice our fundamental unit into much smaller, more digestible increments of time: light seconds, light minutes, and light hours. These smaller increments allow us to chart the solar system with mathematical precision, while revealing just how isolated we are, even within our own planetary family. The nearest cosmic object to Earth is our Moon. It sits at an average distance of approximately 384,000 kilometers. When we calculate how long it takes for a photon to cross this gap, we find that the Moon is a mere 1.3 light seconds away. This means that when you look up at the Moon on a clear night, you are not seeing it as it exists in that exact microsecond. You are looking at a historical record that is 1.3 seconds old. When astronauts stood on the lunar surface during the Apollo missions, their radio communications, which travel at the speed of light, suffered an unavoidable delay. A question asked from Earth took more than a second to arrive, and the answer took just as long to return, creating a strange, disjointed rhythm of conversation dictated entirely by the physics of light travel. As we move outward from the Earth-Moon system, the distances expand dramatically. The centerpiece of our cosmic home is the Sun, located at an average distance of about 150 million kilometers. In astronomy, this distance is defined as 1 astronomical unit. When we apply our velocity formula, we discover that the Sun is approximately 8 light minutes and 20 light seconds away from us. Every single photon of sunlight that warms your skin on a summer day began its journey from the surface of our star more than 8 minutes ago. If the Sun were to suddenly stop shining, we would continue to see it shining brightly in our sky, oblivious to its demise, for nearly 8.5 minutes. This delay creates a strange physical reality. Everything we observe in the cosmos is a snapshot of the past. The farther out we look, the deeper into history we peer. When we look at our neighbouring planet Mars, the delay fluctuates based on our respective orbital positions. At its closest approach, Mars is roughly 3 light minutes away. But when our two planets are on opposite sides of the Sun, that gap widens to over 22 light minutes. This delay makes real-time remote control of Mars rovers completely impossible. NASA engineers cannot steer a rover with a joystick in real time. Instead, they must upload a sequence of commands hours in advance, allowing the spacecraft to navigate autonomously, knowing that if the rover falls into a crater, the signal of its destruction will not reach Earth until long after the event has actually occurred. Travelling even deeper into the outer solar system, the light travel time transitions from minutes to hours. Jupiter, the largest planet in our solar system, sits at an average of 43 light minutes from the Sun. Saturn, with its spectacular ring system, is approximately 1.3 light hours away. Uranus lies about 2.7 light hours out, and Neptune, the windiest ice giant, is situated roughly 4 light hours from the central star. At the cold, dark edge of the planetary realm lies Pluto. Classified as a dwarf planet, Pluto orbits at an average distance of nearly 6 billion kilometers from the Sun. This distance is equivalent to approximately 5.5 light hours. When the New Horizons spacecraft flew past Pluto in July of 2015, it sent its high-resolution images back to Earth via radio signals travelling at the speed of light. It took 4.5 hours for those signals to cross the empty void and register on our deep space antennas. The team of scientists waiting for the data had to endure hours of tense silence, realizing that the spacecraft had already completed its flyby and was rushing into the dark before they even received the first confirmation of its success. Yet, Pluto's orbit does not mark the boundary of our solar system. Far beyond the ice giants and dwarf planets lies a vast, mysterious structure known as the Oort cloud. This is a colossal, spherical shell composed of billions of icy, rocky bodies, believed to be the reservoir for most of our long-period comets. The inner edge of the Oort cloud is estimated to begin at roughly 2,000 astronomical units from the Sun, which is nearly 12 light days away. The outer edge of this massive structure, however, is believed to extend as far as 100,000 astronomical units. When we convert this outer boundary into our primary unit of measurement, we discover that the Oort cloud stretches between 1.5 and 2 full light years into the deep void. It takes nearly 2 years for a photon emitted by the Sun to finally escape the gravitational grip of the Oort cloud and enter the true interstellar medium. This means that the solar system is not a small, compact collection of planets, but a giant sphere of gravitational influence spanning trillions of kilometers across. Inside this cloud, the icy bodies are so far apart that they rarely collide, drifting in near absolute darkness where the Sun appears as nothing more than an exceptionally bright star. Yet, despite this extreme isolation, this region remains an integral part of our home system. It is a transitional zone where the direct influence of our star slowly fades into the background noise of the galaxy. To cross the Oort cloud is to truly leave the sanctuary of our Sun and step into the boundless interstellar ocean, where the distances between objects are no longer measured in minutes or hours, but in agonizingly long light years. Once we completely cross the outer boundaries of the Oort cloud, we find ourselves in the true interstellar medium. This is the vast, silent void that separates the stellar systems of our galaxy. The closest stellar neighbour to our Sun is the Alpha Centauri system, which lies at a distance of approximately 4.24 light years. This means that a beam of light, travelling at 299,792 kilometers per second, must journey through the absolute cold of space for more than 4 years and 3 months to reach us from this neighbouring system. When we look closely at Alpha Centauri, we find it is not a single star, but a triple star system. The two primary stars, Alpha Centauri A and Alpha Centauri B, form a tight binary pair, orbiting each other closely. The third member of this system is a tiny dim red dwarf star, known as Proxima Centauri. Proxima Centauri is actually the closest individual star to our Sun, positioned at that 4.24 light-year mark, slightly closer than its larger companions. Orbiting within the habitable zone of this tiny red dwarf is a fascinating terrestrial world known as Proxima Centauri b, or simply Proxima b. This exoplanet is roughly the size of Earth, and its existence has sparked intense scientific curiosity. If there are oceans or atmospheres on Proxima b, and if some form of life exists on its surface, any visual evidence of that life would take more than 4 years to reach our telescopes. If we were to send a radio message to an imaginary civilization on Proxima b, and they replied immediately upon receiving it, we would have to wait nearly 8.5 years to hear their response. The physical reality of this distance is a heavy, silent barrier to any hope of real-time communication. Imagine a photon of light generated in the nuclear furnace of Proxima Centauri. After fighting its way out of the star's dense plasma interior over thousands of years, it finally escapes into the vacuum of space, heading directly toward Earth. For the first year of its journey, this photon encounters absolutely nothing. It glides through a near-perfect vacuum, where the average density of matter is less than 1 atom per cubic centimetre. The Sun and Proxima Centauri appear as bright, silent points of light in its field of view. By the second year, the photon is deep within the interstellar void, halfway between our two worlds. At this point, the pull of gravity from both stellar systems is incredibly weak, balanced in a cosmic tug-of-war. The photon continues its silent, uninterrupted path, carrying information about the star it left behind. By the third and fourth years, the photon enters the outer reaches of our solar system, crossing the icy reservoir of the Oort cloud. Finally, after travelling nearly 40 trillion kilometres, it enters Earth's atmosphere, pierces the lens of a telescope, and strikes a digital detector or a human retina. The image we see of Proxima Centauri is always more than 4 years out of date. We never see it as it is right now. We only see it as it was when the photon began its long, lonely voyage. If we look further into our stellar neighbourhood, we encounter Sirius, the brightest star in our night sky. Known colloquially as the dog star, Sirius is located in the constellation Canis Major, at a distance of approximately 8.6 light-years from Earth. Sirius is a brilliant white main-sequence star that is twice as massive as our Sun, and shines more than 25 times more brightly. Like Alpha Centauri, Sirius is also a multiple star system, accompanied by a faint white dwarf companion star known as Sirius B. Because Sirius is 8.6 light-years away, the light we see from it tonight left its surface more than 8.5 years ago. If you look at Sirius tonight, you are seeing the star as it existed nearly a decade in the past. The photons striking your eyes began their journey through the void years ago, passing silently through empty space, while human history unfolded on our tiny planet. During the time those photons were travelling to Earth, entire political regimes may have changed, children were born and grew into students, and our own planet completed more than 8 full orbits around the Sun. This delay highlights the profound truth of observational astronomy. The night sky is a living museum. When we look at Alpha Centauri, we see a 4-year-old image. When we look at Sirius, we see an 8.5-year-old image. If we look at other nearby stars, like Procyon at 11.4 light-years, or Altair at 16.7 light-years, we are looking even deeper into the past. Each star we see is a historical broadcast, and because they are all at different distances, we are looking at different eras of history simultaneously. The sky is not a single, unified present moment. It is a tapestry of different pasts, woven together by the varying travel times of photons, crossing the immense interstellar gaps of our neighbourhood. This realization breaks our conventional understanding of time and space, forcing us to accept that in the cosmic arena, distance and history are inextricably linked. As we push our imaginary vessel deeper into the stellar neighbourhood, leaving the familiar glow of our local stars behind, we enter the vast expanse known as the interstellar medium. To the human eye looking up from a dark sky site on Earth, the space between the stars might appear to be a completely empty, pristine void. But to a physicist, this medium is a dynamic, complex, and highly structured environment. It is the raw material from which new stars and planets are born, and it is the graveyard where dying stars deposit their enriched remains. The physical scale of this medium is staggering, but its most shocking attribute is its extreme emptiness. On Earth, we are surrounded by a thick, warm atmosphere. A single cubic centimetre of the air you are breathing right now contains roughly 10 quintillion atoms. This is a density that our bodies and our technologies are finely tuned to navigate. Even the most sophisticated laboratory vacuums created by human engineers on Earth still contain millions of atoms per cubic centimetre. Now, contrast this with the interstellar medium. If you were to take a hollow box measuring 1 centimetre on each side and place it in the deep space between the stars of our galaxy, you would find, on average, only one single atom inside. In some vast regions of the interstellar medium, known as the warm, hot, ionized medium, that density drops even further, down to a mere 1 atom for every 100 cubic centimetres. It is a vacuum so perfect, so absolute, that it makes any vacuum we can produce on Earth look like a dense block of lead. Yet, because the volume of this interstellar space is so colossally large, these sparse, scattered atoms add up to an immense total mass. This material is not uniform. It is divided into distinct phases. There are cold, dense molecular clouds where the density can rise to thousands of molecules per cubic centimetre. These are the stellar nurseries, giant dark complexes of gas and dust, where gravity slowly pulls material together to form new generations of stars. There are also diffuse clouds of neutral hydrogen and vast bubbles of superheated ionized gas, blown by the powerful winds of massive stars and supernova explosions. The composition of this interstellar gas is incredibly simple, reflecting the primordial makeup of the universe. Approximately 90% of the atoms in the interstellar medium are hydrogen, the simplest and most abundant element in existence. Nearly 10% is helium, which was also created in the hot, dense, early phases of the universe. The remaining fraction of a percent consists of trace amounts of heavier elements, which astronomers refer to collectively as metals. These include carbon, oxygen, nitrogen, and iron. These heavier elements were not present at the beginning of the universe. They were forged in the nuclear hearts of ancient stars and scattered across the galaxy when those stars ended their lives in spectacular explosions. In addition to gas, the interstellar medium contains tiny, solid particles known as interstellar dust. These dust grains are not like the dust rabbits you find under your bed, which are mostly composed of dead skin cells and fabric fibers. Interstellar dust consists of microscopic grains of silicates, carbon compounds, and water ice, with sizes typically measuring less than 1 micrometer across. Although dust makes up only about 1% of the total mass of the interstellar medium, it has a profound effect on the light traveling through our galaxy. When a photon of light emitted by a distant star travels through the interstellar medium, it inevitably encounters these tiny dust grains. This encounter leads to 2 primary optical phenomena: extinction and reddening. Extinction is the absorption and scattering of light by dust, which dim the light of distant stars and can block our view of entire regions of the galaxy. Reddening occurs because these microscopic dust grains scatter shorter, blue wavelengths of light much more efficiently than longer, red wavelengths. As a result, the light from a distant star appears redder and dimmer than it actually is by the time it reaches our telescopes, much like the way our atmosphere scatters blue light to create a red sunset on Earth. This interstellar medium is the fabric that fills the majestic disk of our galaxy, the Milky Way. To understand the scale of this disk, we must completely break free from our local coordinates and look at our galaxy from a macroscopic perspective. The Milky Way is a barred spiral galaxy, a grand rotating pinwheel of stars, gas, and dust. When we measure the physical radius of this grand structure, we find ourselves using numbers that defy all human experience. The disk of the Milky Way is estimated to have a diameter of approximately 100,000 light-years. This means that if you were to launch a beam of light from the absolute western edge of the galactic disk, that beam of light would have to travel through the empty, dusty interstellar medium for 100,000 years before it finally emerged from the opposite, eastern edge of the galaxy. To visualize this galactic radius of 50,000 light-years, consider our own position within this structure. Our Sun is not located in the crowded, energetic center of the galaxy, nor is it sitting at the extreme, lonely edge. Instead, we reside in a quiet, suburban neighborhood known as the Orion Cygnus Arm, or simply the Orion Spur. We are positioned roughly 26,000 light-years away from the galactic center. When we look up at the milky band of light stretching across our night sky, we are looking directly into the plane of this disk. We are peering through 26,000 light-years of interstellar gas, dust, and millions of stars toward the core. The light we see from the most distant visible stars in this band did not start its journey during the dawn of human civilization, or even during the last ice age. It has been traveling through the near vacuum of the interstellar medium for tens of thousands of years, carrying a physical record of a distant part of our galaxy that we can only observe from afar. The scale of the Milky Way's radius is so vast that our fastest spacecraft, traveling at tens of thousands of kilometers per hour, would take hundreds of millions of years just to exit the thin disk of our galaxy. The scale is so massive that the entire history of the human species is nothing more than a brief, insignificant flicker compared to the time it takes for light to cross even a small fraction of this galactic expanse. As we contemplate this immense disk of stars and the ultra-low density medium that separates them, we begin to realize that our entire solar system is nothing more than a microscopic speck of dust floating in a titanic, rotating ocean of silence. If we follow the galactic disk inward, toward the very core of the Milky Way, we must travel 26,000 light-years through increasingly dense regions of stars, gas, and dust. At the absolute center of this colossal spiral system lies a region of extreme gravity and intense energy. This is the galactic nucleus, and at its heart sits a monstrous gravitational anchor, a supermassive black hole known to astronomers as Sagittarius A star. This cosmic behemoth contains the mass of approximately 4 million of our suns, packed into a region of space that is smaller than the orbit of Mercury. Because of this extreme concentration of matter, Sagittarius A star possesses a gravitational pull so immense that nothing, not even a photon of light traveling at 299,792 kilometers per second, can escape once it crosses a critical threshold. This point of no return is known as the event horizon. To understand the journey of light near the galactic center, we must look at how extreme gravity affects the behavior of photons. In our everyday lives, we think of light as traveling in perfectly straight lines. But Albert Einstein's theory of general relativity revealed that gravity is not a traditional force pulling on objects. Instead, massive objects warp, bend, and curve the very fabric of space and time around them. When a photon travels through warped spacetime, it continues to follow the shortest possible path, which is called a geodesic. However, because space itself is bent, the path of the light becomes curved. This phenomenon is known as gravitational lensing. Imagine a stream of photons emitted by a bright, highly active star orbiting near the central supermassive black hole. As these photons rush outward, some of them pass very close to the event horizon of Sagittarius A star. As they enter this region of extreme spatial warping, their paths are violently distorted. Instead of travelling in a straight line toward the outer galaxy, the photons are bent around the black hole. If a photon passes too close to the event horizon, inside a region known as the photon sphere, the warping of space is so severe that the light is forced into a circular orbit around the black hole. For a brief moment, these photons orbit the dark center like microscopic satellites, before either spiraling inward to be consumed forever, or being flung outward into the interstellar void at a completely different angle. This severe bending of light creates a stunning optical illusion for astronomers observing the galactic center from Earth. When we look at Sagittarius A star using specialized radio telescope networks, we do not see a simple sphere of darkness. Instead, we see a dark silhouette, the black hole shadow, surrounded by a brilliant ring of light. This ring is composed of photons that have been bent and focused by the gravity of the black hole, creating a distorted, magnified view of the superheated gas swirling around it. This is light that has been literally trapped, twisted, and redirected by the ultimate gravitational engine of our galaxy. Furthermore, as light struggles to escape the immense gravity of the galactic core, it experiences another relativistic effect, known as gravitational redshift. When a photon climbs out of a deep gravitational well, it must expend energy to do so. Because a photon travels at a constant speed and cannot slow down to lose energy, it loses energy by shifting to a longer, lower frequency wavelength. This means that a beam of highly energetic blue or ultraviolet light emitted near Sagittarius A star is stretched and shifted toward the red and infrared end of the electromagnetic spectrum as it fights its way out of the galactic core. By the time this light escapes the intense gravity of the center and begins its 26,000 light-year journey to Earth, its physical properties have been completely altered by the gravity of the supermassive black hole. Once these warped, shifted photons finally break free from the chaotic environment of the galactic core, they must navigate the dense, crowded stellar populations of the inner galaxy. In the central nuclear star cluster, stars are packed together millions of times more densely than they are in our quiet solar neighborhood. The sky of an imaginary planet located near the galactic core would be ablaze with thousands of stars shining as brightly as our full moon, casting a brilliant, eternal daylight across the landscape. As our stream of photons travels outward, it passes through these crowded stellar highways, slowly leaving the energetic center behind. It travels through the thin disk of the galaxy, passing giant stellar nurseries, dying supernova remnants, and cold molecular clouds, each obstacle scattering or absorbing some of the light, carving away information about its origin. For 26,000 years, this light travels through the silent, near-empty void of the interstellar medium. To put this timescale into perspective, when these photons first escaped the gravity of Sagittarius A star and began their journey toward our solar system, humanity was in the midst of the last ice age. Our ancestors on Earth were hunters and gatherers, surviving in a harsh world of mammoths and glaciers, with no concept of telescopes, physics, or the massive galaxy they inhabited. While those photons were silently gliding through the dark space between the stars, human civilization rose from the dust. We developed agriculture, built the pyramids of Egypt, wrote down our first laws, established global empires, split the atom, and launched our first primitive satellites into orbit. All of human history occurred in the brief interval it took for those photons to cross just one fraction of our galaxy's radius. When those warped, redshifted photons finally arrive at Earth and strike the sensitive detectors of our modern telescopes, they carry with them the physical imprint of their violent birth near the supermassive black hole. By analysing the angles of their arrival and the degree to which their wavelengths have been stretched, scientists can reconstruct a highly detailed image of the environment surrounding Sagittarius A star. We are able to peer directly into the heart of our galaxy and watch stars orbiting the central dark mass at incredible speeds, guided by the same gravitational warping that bent the light we are observing. This light is a cosmic messenger, bearing witness to the extreme physics of the galactic core, and reminding us that the centre of our galactic home is a place where space, time and light are bent to the breaking point by the power of a 4 million solar mass monster. To truly understand our place in the cosmos, we must confront a mind-bending physical reality. We can never see the universe as it exists in the present moment. This is not a limitation of our technology, nor is it a flaw in our biological senses. It is a fundamental law of physics, dictated by the finite speed of light. Because photons take time to travel across the vast gulfs of space, looking out into the night sky is literally looking backward in time. Every star, every nebula, and every galaxy we observe is a ghostly transmission from a past epoch, making the sky the ultimate, natural cosmic time machine. To understand how this optical time machine works, we must look at the basic physics of sight. When you look at an object in your room, say a book resting on a table, you do not see the book instantly. You see the book because light from a lamp or the sun bounced off its surface and travelled to your eyes. Because the distance is only a few meters, the time it takes for those photons to reach you is less than a billionth of a second. This delay is so incredibly small that your brain processes it as instantaneous. For all practical purposes on Earth, the past and the present are identical. But as we lift our gaze to the heavens, the distances swell to scales where this delay becomes impossible to ignore. The Moon, as we have established, is viewed at a delay of over 1 second. The Sun is a snapshot from over 8 minutes ago. When we look at the giant planet Jupiter, we are looking at its state nearly 3/4 of an hour in the past. If a massive volcanic eruption were to rip through the icy crust of its moon Europa at this very moment, we would have no way of knowing. We would have to sit patiently on Earth for 45 minutes, waiting for the first photons carrying the visual evidence of the explosion to finish their long journey through the freezing vacuum. When we look beyond our solar system, the time delays stretch from minutes to years, decades, and centuries. The stars we see with our naked eyes on a clear night belong to our local galactic neighbourhood, yet they are still unimaginably distant. Vega, one of the brightest stars in the northern sky, sits at a distance of 25 light-years. When you look at Vega tonight, you are seeing it as it was 25 years ago, in the early years of the 21st century. The photons entering your eyes began their journey when the internet was still in its infancy, and mobile phones were bulky devices. If we look further, we see Deneb, a brilliant supergiant star in the constellation Cygnus. Deneb is located approximately 2,600 light-years from Earth. This means the light striking your eyes from Deneb tonight left that star more than 2.5 millennia ago. Those photons began their journey through the interstellar medium during the height of the classical Greek civilization, long before the rise of the Roman Empire. While those photons were silently gliding through the empty void of space, entire empires on Earth rose, conquered, crumbled, and faded into history. This physical reality means that the night sky is not a single unified moment in time. Instead, it is a deeply layered, three-dimensional tapestry of different histories. When you look up, you are looking at a composite image made of different eras mixed together. A star that is 10 light-years away is seen as it was 10 years ago. A star right next to it that is 1,000 light-years away is seen as it was 1,000 years ago. Some of the massive, highly unstable stars we observe in distant nebulae may not even exist anymore. They may have already run out of fuel and exploded as brilliant supernovae. But because the light of their destruction is still travelling across the vast gulf of space, we will continue to see them shining peacefully in our sky for thousands of years to come. This principle becomes the primary tool for modern astrophysics. By building larger and more powerful telescopes, like the Hubble Space Telescope and the James Webb Space Telescope, we are not just magnifying distant objects to see them more clearly, we are physically pushing our vision deeper into the past. A telescope is, in the most literal sense, a light bucket. It collects ancient, faint photons that have been travelling across the universe for millions or billions of years. By focusing these cosmic messengers onto sensitive electronic sensors, we can capture images of the universe as it existed during its infancy. When we point our telescopes at the Andromeda galaxy, which lies 2.5 million light-years away, we see it as it existed before the first modern humans walked the Earth. When we peer at ultra-distant galaxies located 10 billion light-years away, we are looking at a time when our own solar system did not even exist. We are seeing those galaxies as they were when the universe was only a fraction of its current age, still raw, chaotic, and bursting with new star formation. This natural time machine allows us to write the history of the universe not through guesswork or theoretical models, but through direct observation. We do not have to wonder how galaxies evolved over billions of years. We can simply look at different distances and watch them grow. We can compare a galaxy seen at a delay of 1 billion years with a galaxy seen at a delay of 10 billion years, observing the structural changes, the chemical enrichment, and the life cycles of stars directly. It is a beautiful, deeply humbling paradox. The very thing that prevents us from ever knowing what the universe looks like right now is the exact tool that allows us to see where we came from. The finite speed of light locks us out of the present, but it opens the door to the deep, majestic past. We are forever looking back, tracing the long, silent pathways of ancient photons to piece together the grand story of our cosmic origins, one light-year at a time. To truly appreciate the mind-breaking nature of cosmic distances, we must examine what happens when we attempt to conquer them. If humanity were to ever build a spacecraft capable of travelling near the speed limit of the cosmos, we would run headfirst into one of the most famous and unsettling predictions of Albert Einstein's physics: time dilation. Time is not a universal constant that ticks at the same rate for everyone, everywhere. Instead, time is elastic. It stretches and contracts depending on how fast you are moving through space. If you were to board a ship and travel across the Milky Way at 99% of the speed of light, you would experience a physical reality so strange it sounds like science fiction, yet it is a mathematical certainty. To understand this relativistic journey, we must first look at the mathematical relationship between speed and time, defined by the Lorentz factor. When you travel through space, your motion is a trade-off. You are always moving through a four-dimensional construct called space-time. The faster you move through the three spatial dimensions, the slower you must move through the fourth dimension of time. At ordinary everyday speeds, like driving a car or flying in a commercial airplane, this effect is so tiny that it is completely imperceptible, requiring ultra-precise atomic clocks to detect even a fraction of a microsecond of difference. But as you accelerate to relativistic speeds, the physics changes dramatically. When your spaceship reaches exactly 99% of the speed of light, the mathematics of special relativity dictates that time for you will slow down by a factor of approximately 7. This means that for every 7 hours that pass for an observer sitting quietly on Earth, only one single hour ticks away on your spaceship's onboard clocks. Your heartbeat, your cellular aging, the processing speed of your brain, and the vibration of the atoms in your ship's computer all slow down in perfect synchronization relative to the universe outside. Now, imagine using this technology to embark on a grand voyage across the entire disk of our galaxy, a distance of approximately 100,000 light-years. To an observer remaining behind on Earth, the physics of your trip is straightforward. They watch your ship fire its engines and accelerate until it is travelling at 99% of the speed of light. Because you are travelling just under the speed limit, they calculate that it will take you slightly over 100,000 years to cross the galaxy. Over this vast interval, generations of humans will pass, civilizations will rise and crumble into dust, and the very geography of Earth will slowly shift as tectonic plates drift. To the people of Earth, you are on an epic, epoch-spanning journey that outlasts human history. But inside the cockpit of your spaceship, your experience is completely different. You do not feel like you are moving in slow motion. If you pour a cup of water, it falls normally. If you speak, your voice sounds normal. To you, your local time is running perfectly. Yet because of your extreme velocity, the space in front of your ship undergoes a phenomenon called length contraction. The universe physically squashes itself along your direction of travel. The vast 100,000 light-year distance of the galactic disk is suddenly compressed by that same factor of 7. To your senses, the galaxy is no longer 100,000 light-years wide. It has shrunk to a much more manageable 14,000 light-years. Consequently, when you check your calendar upon reaching the far side of the galaxy, you will find that only 14,000 years have passed for you and your crew. You have crossed the entire Milky Way within a time span that is shorter than the history of human agriculture, while the universe you left behind has aged by over 100,000 years. The physical experience of looking out the window during this high-speed voyage would be utterly alien. In popular science fiction, travelling at near light speed is often depicted as stars stretching out into long, beautiful, glowing lines. In reality, the visual physics of relativity is far more chaotic. Because you are rushing toward the light emitted by the stars ahead of you, those photons are compressed into much shorter, higher energy wavelengths. This is relativistic blue shift. The starlight in front of you is transformed from visible light into intense, blinding ultraviolet rays, X-rays, and gamma rays. The stars in front of you do not stretch. Instead, they seem to crowd together, bending toward the center of your field of view in an optical effect called relativistic aberration. The stars behind you are stretched into longer, lower energy wavelengths, redshifting into the infrared spectrum and fading into complete darkness. The cosmic sky is transformed into a singular, intensely bright ring of highly concentrated, violet-white energy dead ahead, surrounded by a dark, frozen void. Furthermore, traveling at 99% of the speed of light turns the empty interstellar medium into a deadly shooting gallery. As we established, the space between stars contains roughly 1 atom of hydrogen per cubic centimeter, along with microscopic dust grains. At ordinary speeds, this material is completely harmless. But when your ship collides with these stationary atoms at 99% of the speed of light, the relative kinetic energy is catastrophic. Each individual hydrogen atom strikes your ship's hull with the force of a cosmic ray particle, generating intense, penetrating radiation. A single microscopic grain of dust, weighing only a fraction of a milligram, would impact your shield with the kinetic energy of a massive explosive device. Without advanced, highly theoretical shielding to deflect or absorb this endless, high-velocity atomic bombardment, your ship and your body would be vaporized within seconds of reaching cruising speed. If you were to complete your journey across the galaxy, turn your ship around, and fly another 14,000 years of ship time back to Earth, the true tragedy of the relativistic paradox would be waiting for you. While you and your crew have aged by only 28,000 years, more than 200,000 years have passed on your home planet. The world you left behind would be completely unrecognizable. The people who waved goodbye to you are not just dead. Their entire cultures, languages, and cities have been buried under layers of geological sediment. Your journey through space was also a one-way trip into the far future. This is the ultimate physical barrier of the light year. Even if we can warp time to shorten the journey for the travelers, the universe refuses to let us share those discoveries in real time, forever separating the explorers from the world they once called home. To truly understand the breakdown of human scale, we must now take the ultimate leap and leave our home galaxy entirely. As we rise above the majestic, swirling disk of the Milky Way, we enter a realm of near absolute nothingness, the intergalactic void. If you thought the space between stars was empty, the space between galaxies is a completely different level of desolation. In this vast, cold abyss, the density of matter drops to less than 1 single atom per cubic meter. It is a silent, frozen desert that stretches for millions of light years, separating the brilliant island universes of the cosmos. Looking out across this terrifyingly empty intergalactic ocean, our eyes are drawn to a massive, glowing spiral of stars. This is the Andromeda galaxy, also known to astronomers as Messier 31. Andromeda is the closest major galaxy to our own, and it is the most distant object that a human being can see with the naked eye from a dark location on Earth. Yet, the word close is entirely relative in the grand architecture of the universe. Andromeda lies at a distance of approximately 2.5 million light-years from us. To comprehend this distance, we must once again look at the travel time of light. The photons from Andromeda that strike your eyes tonight have been travelling through the deep intergalactic void for 2,500,000 years. They began their journey during the Pleistocene epoch, long before modern humans had even evolved on Earth. Our distant ancestors, Australopithecus, were walking the African savannas when these photons first escaped the outer stars of the Andromeda galaxy. For 2.5 million years, while species rose and fell, and ice ages advanced and retreated across our planet, this light silently glided through the pitch-black intergalactic vacuum, finally ending its epic journey on your retina. But Andromeda is not just a distant, beautiful object to be admired from afar. It is also on a direct collision course with the Milky Way. When we analyse the light coming from Andromeda, we find that it does not exhibit the redshift characteristic of the expanding universe. Instead, it shows a distinct blue shift. This physical measurement tells us that Andromeda and the Milky Way are rushing toward each other, drawn together by their immense, mutual gravitational attraction. Andromeda is hurtling toward our galaxy at a staggering speed of approximately 110 kilometers per second. This is equivalent to nearly 400,000 kilometers per hour. Even at this incredible velocity, the distance of 2.5 million light-years is so vast that the collision will not happen anytime soon. It will take approximately 4 to 5 billion years for the two giant galaxies to finally meet. The physics of this future galactic merger, which astronomers have nicknamed Milkdromeda, will be one of the most spectacular events in the history of our local universe. As the outer halos of dark matter and gas from the two galaxies begin to touch, the gravitational interaction will trigger immense changes. The elegant spiral structures of both galaxies will be violently disrupted. Powerful gravitational tidal forces will pull out long glowing tails of stars, gas and dust, stretching them across hundreds of thousands of light-years of space. Yet, despite the violent nature of this event, the individual stars within both galaxies will almost certainly never collide. This is because of the extreme emptiness of space that we explored earlier. Although each galaxy contains hundreds of billions of stars, the physical distance between those stars is so immense that they are like lonely dust motes floating in a giant auditorium. When the two galaxies merge, they will pass through each other like two silent ghosts. The stars of Andromeda will slide harmlessly into the vast empty gaps between the stars of the Milky Way. However, the giant clouds of interstellar gas and dust within both systems will not escape so easily. As these massive molecular clouds collide at high speeds, they will compress and heat up. This sudden, violent compression will spark a tremendous wave of new star formation. The merged galaxy will temporarily become a starburst galaxy, lit up by millions of brilliant, massive, short-lived blue stars, illuminating the cosmic clouds. Over the course of several billion years, the gravitational chaos will slowly settle down. The two distinct spirals of the Milky Way and Andromeda, along with their smaller satellite galaxies, will merge into a single, massive, featureless elliptical galaxy. If any descendants of humanity are still alive on a planet orbiting our Sun in 5 billion years, their night sky will be completely transformed. The familiar thin band of the Milky Way will be gone, replaced by a brilliant, diffuse glow of trillions of stars surrounding the planet in all directions. This future collision is a powerful reminder of the dynamic, ever-changing nature of the cosmos. The light year is not just a static ruler that measures how far apart we are from our neighbours. It is a timeline that dictates when these titanic gravitational interactions will occur. As we look across the 2.5 million light-years of intergalactic space that currently separate us from Andromeda, we are looking at both a distant mirror of our own galaxy and a preview of our ultimate shared destiny. As we expand our field of view even further, rising above the impending collision between the Milky Way and the Andromeda galaxy, we begin to perceive a much larger structure. This is our local cosmic neighbourhood, a gravitationally bound collection of stellar systems known to astronomers as the local group. Spanning a physical diameter of approximately 10 million light-years, This structure represents our immediate family in the grand architecture of the universe. Within this vast volume of space, a delicate, invisible tug-of-war is taking place between two of the most powerful forces in physics: the inward pull of mutual gravity and the outward stretching force of the expanding universe. To understand the physics of the local group, we must first look at its members. This cosmic cluster is not dominated by a single giant system. Instead, it is a binary system of two massive heavyweights, the Milky Way and the Andromeda galaxy, which contain the vast majority of the cluster's total mass. Surrounding these two giant spirals is a swirling entourage of more than 50 smaller, dwarf satellite galaxies. These include familiar systems like the large and small Magellanic Clouds, which orbit the Milky Way, as well as Messier 32 and Messier 110, which cling to the gravitational field of Andromeda. Each of these satellite galaxies is a collection of millions or billions of stars, yet they are dwarfed by their massive hosts, slowly being stripped of their gas and dust by the relentless tidal forces of the larger spirals. When we measure the physical scale of the local group, the light travel times become truly staggering. To cross from one end of this cluster to the other, a photon of light must travel through the intergalactic vacuum for 10 million years. This means that if a catastrophic event, such as a supermassive black hole flare or a massive starburst, were to occur in a dwarf galaxy on the far eastern edge of the local group today, the light from that event would not reach Earth until the year 10,000,2026. Our planetary home, our solar system, and our entire civilization would have aged by 10 million years before we could ever witness the first cosmic signal of the event. We are looking at our cosmic family through a thick, ancient veil of time delay. Yet the most fascinating physical characteristic of the local group is its ability to resist the expansion of the universe. In the late 1920s, astronomer Edwin Hubble made the revolutionary discovery that the universe is expanding. He observed that distant galaxies are rushing away from us, and the farther away they are, the faster they are receding. This expansion is not caused by galaxies physically flying through space. Instead, it is the fabric of space itself that is stretching, expanding in all directions like a massive balloon being inflated. If this expansion were the only physical process at play, every galaxy in the universe would slowly drift away from every other galaxy, leaving every stellar system completely isolated in a dark, empty void. But the universe is also governed by gravity. Gravity is an attractive force that arises from the presence of mass and energy, warping space-time to pull objects together. According to the laws of general relativity, the expansion of space is a global property, but its strength can be overcome on local scales if there is enough mass concentrated in a specific region. This is the exact physical reality of the local group. The total mass of the Milky Way, Andromeda, and their dozens of satellite galaxies, combined with the invisible scaffolding of dark matter that surrounds them, is immense. It is estimated to be equivalent to more than 2 trillion times the mass of our Sun. This colossal concentration of mass creates a gravitational well so deep that it physically halts and reverses the expansion of space within its boundaries. Inside this 10 million light-year sphere, gravity is the undisputed king. The galaxies of the local group are locked in a tight, eternal gravitational embrace. Bounded by their mutual attraction, they are physically falling toward one another, defying the cosmic stretch that is tearing the rest of the universe apart. While more distant galaxies outside our group are being swept away from us by the expansion of space, the members of our local group will remain together forever. This gravitational binding has a profound, bittersweet implication for the far future of our cosmic neighborhood. As the billions of years unfold, the expansion of the universe will continue to accelerate, driven by the mysterious force known as dark energy. Galaxies that lie outside the boundary of our local group will be pushed farther and farther away from us, moving faster and faster until they eventually cross our cosmic horizon. Their light will no longer be able to reach us, and they will fade from our view, vanishing into the cold, unobservable dark. Ultimately, every single galaxy outside of our 10 million light-year neighborhood will disappear from our sky. But within the local group, the story is entirely different. Because we are gravitationally bound, the Milky Way, Andromeda, and all of their satellite companions will slowly merge over the eons, consolidating their stars, gas, and dark matter into a single, massive, supergalactic system. The local group is our permanent home, a self-contained cosmic sanctuary where gravity has built an unbreakable wall against the endless stretch of the expanding universe, ensuring that we will never be truly alone in the deep dark of the cosmos. To understand the true shape of the cosmos on the grandest possible scale, we must look far beyond our 10 million light-year local group. If we could zoom out until our entire home galaxy became a microscopic point of light, we would see that the universe is not a chaotic, disorganized scattering of stars and galaxies. Instead, it is arranged in a titanic, majestic, three-dimensional structure known as the cosmic web. This cosmic web is the largest known structure in existence, a colossal network of matter that resembles the complex neural pathways of a human brain, or a delicate, glowing spiderweb stretched across the infinite dark. In this macroscale architecture, galaxies are not isolated. Instead, they are strung along immense glowing threads called cosmic filaments. These filaments are massive bridges of gas, dust, dark matter, and trillions of stars that stretch across hundreds of millions of light years. They are the superhighways of the universe, channeling matter and guiding the motion of galaxies over cosmic time. Where these massive filaments intersect, they form dense, incredibly bright nodes. These nodes are superclusters, the largest gravitational structures in the cosmos. Between these dense filaments lie vast, pitch-black expanses of near-absolute nothingness called cosmic voids, which contain almost no matter at all. Our own stellar home belongs to one of these titanic superclusters, a structure of mind-boggling scale known as Laniakea. The name Laniakea is derived from a Hawaiian term meaning immeasurable heaven, a highly fitting description for a structure that spans approximately 520 million light-years from one end to the other. To cross this immense supercluster, a single photon of light, travelling at its absolute speed limit, must journey through the intergalactic void for more than 500 million years. Laniakea is not a solid object, but a massive watershed of gravity. It contains more than 100,000 individual galaxies, including the Milky Way and the Andromeda galaxy, all bound together by gravity. If we map the motions of these 100,000 galaxies, we find that they are all flowing along invisible gravitational pathways, like streams of water trickling down a mountain toward a singular, immensely massive gravitational center known as the Great Attractor. The Great Attractor is a mysterious, highly concentrated anomaly located in the direction of the Centaurus constellation, pulling our entire region of the universe toward it at hundreds of kilometers per second. Yet this majestic cosmic web and the giant structure of Laniakea could not exist without an invisible, mysterious ingredient that dominates the physics of the macrocosmos. This is dark matter. Dark matter is one of the greatest mysteries in modern science. It does not emit, absorb, or reflect light, making it completely invisible to every type of telescope humanity has ever built. It does not interact with the electromagnetic force, meaning we cannot touch it, see it, or measure it directly. Yet we know it exists because of its profound gravitational influence on the visible matter around it. In fact, normal matter, the gas, dust, stars, planets, and human beings that we can see and touch, makes up only about 15% of the total matter in the universe. The remaining 85% of the matter is dark matter. On the largest scales, dark matter acts as the invisible scaffolding of the entire universe. During the early phases of the cosmos, dark matter clumped together under the influence of gravity, forming massive, invisible halos and long, thread-like structures. It was this dark matter scaffolding that pulled in the normal, baryonic hydrogen gas, allowing it to pool, compress, and ignite to form the first stars, galaxies, and cosmic filaments of the web. Without the gravitational glue of dark matter, the expanding universe would have scattered normal matter too thin to ever form galaxies, leaving the cosmos a cold, featureless, and dark soup. Even though dark matter is completely invisible, it has a profound and measurable effect on the light travelling through Laniakea and the cosmic web. Because dark matter possesses immense mass, it warps the fabric of space-time surrounding the cosmic filaments. When ancient photons emitted by ultra-distant galaxies travel across the universe to reach our telescopes, they must pass through these massive concentration zones of dark matter. As the light travels through the warped space-time of a filament, Its path is bent, twisted, and focused by the gravity of the invisible matter. This phenomenon of gravitational lensing allows astronomers to map the invisible cosmic web with incredible precision. By observing how the light from extremely distant galaxies is distorted, stretched, and magnified as it passes through the foreground filaments, scientists can calculate the exact shape and mass of the dark matter that caused the distortion. It is as if the universe has provided us with a giant natural magnifying glass, using the gravity of invisible matter to bend the path of light and reveal the underlying structure of the cosmos. When we look at Laniakea through the lens of this cosmic web, we realize that our Milky Way is not a lonely wanderer in the dark. We are intimately connected to a vast, flowing river of stars and invisible matter. The light that travels through this web is constantly being bent and shaped by the gravitational pull of dark matter, tracing the contours of an invisible empire that shapes the destiny of everything we can see. On this macro scale, the light year ceases to be just a measure of distance between stars. It becomes the scale on which the very skeleton of the universe is revealed, showing us that we are part of a grand, interconnected tapestry of light and shadow stretching across the deep, silent void. While the cosmic web is defined by its massive, glowing filaments of dark matter and trillions of stars, it also contains a dark, terrifying counterpoint. These are the cosmic voids. If the filaments are the bustling highways of the universe, the voids are its grand, silent deserts. They are colossally large, spherical expanses of near absolute nothingness that lie between the glowing threads of the cosmic web. In these desolate regions, the density of matter drops to near zero, creating a physical environment of isolation and darkness that is almost impossible to comprehend. And among these vast oceans of emptiness, one stands out as the ultimate monument to cosmic desolation, the Boötes Void. Discovered in 1981 by astronomer Robert Kirshner and his team, the Boötes Void is one of the largest known voids in the entire observable universe. It is often referred to by astronomers simply as the Great Nothing. This colossal sphere of emptiness is located in the direction of the Boötes constellation, and it spans an unbelievable physical diameter of approximately 330 million light-years. To visualize this scale, consider the journey of light. A single photon travelling at its absolute speed limit of 299,792 kilometers per second would take 330 million years to cross from one side of this void to the other. If you were to drop the entire Milky Way galaxy into the middle of the Boötes Void, it would look like a tiny, lonely speck of dust, lost in a massive, dark mansion, completely swallowed by the surrounding darkness. In a normal, average region of the universe of this size, we would expect to find thousands of bright, massive spiral and elliptical galaxies, each containing hundreds of billions of stars. If we look at a typical volume of space with a diameter of 330 million light-years, we would normally see about 10,000 galaxies glowing in the dark. Yet when astronomers point our most sensitive telescopes toward the heart of the Boötes Void, they find almost nothing. Across this entire immense 330 million light-year expanse, scientists have managed to discover only about 60 individual galaxies. These rare, isolated systems are scattered across the vast emptiness, like lonely survivor outposts in a post-apocalyptic wasteland, separated from one another by distances that make our own intergalactic gaps look incredibly crowded. The extreme isolation of these rare galaxies within the Boötes Void has a profound effect on how they evolve. In the crowded environment of cosmic filaments, galaxies constantly interact, collide, and merge, pulling in fresh hydrogen gas to fuel the birth of new stars. But inside the Great Nothing, the 60 isolated galaxies are completely cut off from this cosmic nourishment. With no nearby companions to collide with, and no massive filaments to channel fresh gas toward them, these galaxies must rely solely on their own limited resources. They grow slowly and quietly, drifting through the dark vacuum in near absolute solitude, far away from the energetic, evolving core of the cosmic web. For a human observer, the psychological and physical reality of being inside the Boötes Void would be truly terrifying. Imagine standing on an imaginary planet, orbiting a star inside one of the rare galaxies located at the very center of the Great Nothing. If you were to look up at the night sky from this planet, you would not see a majestic glowing band of stars like our Milky Way. nor would you see the faint, beautiful shapes of distant neighbouring galaxies. Instead, you would look out into a pitch-black, featureless and infinite abyss of absolute darkness. The sky would be completely empty. The distance to the nearest neighbouring galaxy would be so immense that its light would be too faint to detect with the naked eye. In fact, the isolation is so complete that if the Milky Way had been located at the centre of the Boötes Void, humanity would not have discovered the existence of other galaxies until the 1960s. We would have spent centuries believing that our galaxy was the sole, lonely island of light in an otherwise completely dark and empty universe. The sheer lack of nearby structures would have severely delayed our understanding of cosmology and the true scale of the universe we inhabit. This absolute absence of light and matter inside the Boötes Void is not just a passive physical state, it is a direct consequence of the gravitational dynamics of the cosmic web. Over billions of years, the universe has undergone a process of gravitational drainage. During the early phases of the cosmos, the regions that had slightly more matter used their superior gravity to pull in more gas and dust from their surroundings. As these matter-rich regions grew into the massive filaments and superclusters we see today, they literally sucked the material out of the surrounding areas. The regions that had slightly less matter to begin with were cleared out, losing their gas, dust and galaxies to the growing gravitational powerhouses nearby. The Boötes Void is the ultimate result of this cosmic bullying, a region of space that has been completely emptied of its raw materials, leaving behind a cold, dark and silent monument to the power of gravity. As we contemplate the 330 million light-years of empty space that make up the Boötes Void, we are forced to confront the true meaning of emptiness. We often think of the universe as a place crowded with brilliant stars, colourful nebulae, and swirling galaxies, but the existence of the Great Nothing reveals that the dominant feature of our universe is actually empty space. The brilliant structures we love to observe are nothing more than rare, delicate exceptions in a vast, silent, and endless ocean of darkness. The Boötes Void is a chilling reminder of the cold reality of the cosmos, a place where light and life are almost completely absent, and where the silence of the vacuum stretches across hundreds of millions of light-years without a single star to break the dark. As we push our vision past the colossal emptiness of the Boötes Void, we find ourselves approaching the ultimate boundary of our reality. This is the edge of the observable universe, a physical horizon that marks the absolute limit of what we can ever see or know. At this extreme threshold, the concepts of space, time, and the speed of light collide to create a spectacular physical paradox. To understand this final frontier, we must explore two of the most profound discoveries in modern astrophysics: the cosmic microwave background radiation and the mind-expanding reality of an expanding space-time that can outrun light itself. If we want to peer back to the very beginning of our universe, we must look at the oldest light in existence. This is the cosmic microwave background, which physicists often refer to as the cosmic microwave background radiation. Approximately 13.8 billion years ago, our universe began in a hot, dense, and energetic state known as the Big Bang. For the first 380,000 years of its existence, the universe was so hot that atoms could not form. Instead, it was a thick, opaque soup of superheated plasma, composed of free electrons and protons. Photons of light were constantly colliding with these free electrons, unable to travel more than a fraction of a millimeter without being scattered. The entire universe was a glowing, white-hot fog, completely opaque to any form of observation. But as the universe expanded, it slowly cooled. When the temperature dropped to approximately 3000 Kelvin, a major physical transition occurred, known as recombination. Protons and electrons finally joined together to form the first neutral hydrogen atoms. Because these neutral atoms did not scatter light the way free electrons did, the universe suddenly became transparent. The ancient photons of the Big Bang, which had been trapped in the plasma fog for hundreds of thousands of years, were suddenly set free. They began their long, uninterrupted journey through space, a flash of primeval light released simultaneously from every point in the cosmos. As this ancient light travelled across the expanding universe for 13.8 billion years to reach our modern telescopes, the space it travelled through was constantly stretching. This cosmic expansion stretched the wavelengths of those ancient photons, shifting them from highly energetic, visible, orange-yellow light all the way down into the invisible microwave region of the electromagnetic spectrum. Today, this light bathing our planet from every direction is the cosmic microwave background. It is a baby picture of our universe, a physical record of the first light that ever escaped the primeval plasma, carrying the structural blueprint of the cosmos when it was only 380,000 years old. But this ancient light also brings us face to face with a deep mathematical paradox. If the universe is exactly 13.8 billion years old, you might naturally assume that the farthest we can look in any direction is 13.8 billion light years. This would mean that the total diameter of our observable universe should be 27.6 billion light years. But when astrophysicists calculate the actual physical distance to the edge of the observable universe, they find a number that is much larger, approximately 46 billion light years in every direction, resulting in a total observable diameter of 93 billion light years. How is this physically possible? How can we see an object that is 46 billion light years away if light has only been travelling for 13.8 billion years? The answer lies in the dynamic physics of space expansion, defined by the laws of general relativity. Space is not a static, empty stage. It is a flexible, dynamic fabric that can stretch, expand, and bend. When we say the universe is expanding, we do not mean that galaxies are physically moving away from each other through an existing empty space. Instead, new space is constantly being created between those galaxies. To understand how this affects light, imagine an ant walking along a rubber band at a constant speed of 1 centimeter per second. If you hold the ends of the rubber band and stretch it while the ant is walking, the ant will take much longer to reach the other side. More importantly, the physical distance between the ant's starting point and its destination will increase during its journey. This is exactly what happens to a photon of light travelling across the universe. As the photon rushes toward Earth, the space behind it and the space in front of it are constantly stretching. By the time the photon finally reaches our telescopes, the galaxy that originally emitted that photon 13.8 billion years ago has been pushed much farther away by the expansion of space, currently residing at a physical distance of 46 billion light years. This expansion of space leads to an even more shocking physical reality. Space can stretch faster than the speed of light. In the framework of special relativity, nothing can travel through space faster than 299,792 kilometers per second. This is the absolute local speed limit. But this limit does not apply to the expansion of space itself. General relativity imposes no speed limit on how fast the fabric of spacetime can stretch. In the modern universe, at extremely large distances, the cumulative expansion of space is so great that distant galaxies are moving away from us at velocities that exceed the speed of light. This boundary is known as the Hubble horizon. Galaxies located beyond this horizon are receding from us faster than light, meaning that any new photons they emit today can never reach us. They have passed beyond our cosmic horizon, vanishing forever into the unobservable universe. This creates a bittersweet boundary for humanity. The observable universe, with its 93 billion light-year diameter, is only a tiny fraction of the entire infinite cosmos. Beyond our observable horizon, there are trillions of other galaxies, stars, and physical structures that we will never see, touch, or explore. The finite speed of light has built an absolute wall around us, a physical boundary that defines the limits of our observable reality, reminding us that we are floating on a tiny island of light, surrounded by an endless, unobservable ocean of space. When we measure the mind-breaking scale of the cosmos in light years, we are forced to look back at our own tiny planet and ask a difficult question. What are we doing to cross these immense abysses of empty space? When we examine the history of human spaceflight, the contrast between the vast scale of the universe and our current technology is both deeply humbling and inspiring. We have taken our first tentative, microscopic steps into the dark, but our physical efforts only highlight the true scale of the cosmic prison we are trying to escape. The prime example of our current physical limits is the Voyager 1 spacecraft. Launched by NASA in September of 1977, Voyager 1 was designed to study the outer planets of our solar system. After completing its primary mission, it kept hurtling outward, eventually crossing the heliopause and entering the interstellar medium in August of 2012. It is currently the most distant human-made object in existence. Yet, when we convert its legendary journey into the metrics of light travel, the results are shocking. After travelling through space for nearly half a century at a velocity of over 61,000 kilometers per hour, Voyager 1 is only about 22.5 light-hours away from Earth. It has not even crossed a single light day of distance. To put this into perspective, if Voyager 1 were heading directly toward our nearest stellar neighbour, the Alpha Centauri system, it would take the spacecraft more than 75,000 years of continuous travel to cross those 4.24 light-years of space. Our fastest physical machines are barely crawling through the interstellar dark. To break free from this local scale, scientists and engineers are looking to revolutionary, highly theoretical propulsion concepts that could allow us to travel at a fraction of the speed of light. The most promising near-term proposal is the Breakthrough Starshot project. Instead of relying on heavy chemical rockets, which must carry their own fuel, this concept proposes using a ground-based laser array to propel a fleet of ultra-lightweight microchips attached to extremely thin, reflective sail structures, known as light sails or laser sails. By focusing a giant 100 gigawatt laser beam onto these sails for just a few minutes, we could theoretically accelerate the tiny probes to approximately 20% of the speed of light. At this incredible velocity, the probes could cross the 40 trillion kilometer gap to Alpha Centauri in just over 20 years, capturing the first close-up images of Proxima b and transmitting them back to Earth via laser signals, which would take another 4 years to arrive. It is a bold, highly complex engineering challenge that could provide our first real-time data from another stellar system within our lifetimes. But what if we want to send human beings, not just tiny microchips, across the light years? To transport massive, biological payloads without waiting decades or centuries, we would need to find a loophole in the absolute speed limit of the universe. This has led theoretical physicists to explore one of the most exciting, mind-bending concepts in general relativity, the Alcubierre warp drive. First proposed by Mexican physicist Miguel Alcubierre in 1994, this theoretical propulsion system does not attempt to push a spaceship through space faster than light, which, as we established, is physically impossible. Instead, the warp drive manipulates the fabric of space-time itself. According to general relativity, space can expand and contract at any speed. The Alcubierre metric proposes creating a wave of space-time warping that contracts the space in front of the ship while expanding the space behind it. The spaceship itself would sit safely inside a flat region of space-time known as a warp bubble. Within the space inside the bubble, the ship is completely stationary, meaning it violates no local laws of special relativity and suffers none of the catastrophic kinetic effects of near-light travel. Yet the bubble itself would ride the wave of expanding and contracting space-time, moving at any arbitrary speed, theoretically allowing us to travel across light-years of space in a matter of days or weeks from the perspective of both the crew and Earth. However, the physics of building a functioning warp drive presents monumental challenges. To create the negative curvature of space-time required to expand space behind the ship, the Alcubierre warp drive requires a highly exotic theoretical form of energy known as negative energy density, which would be produced by using exotic matter. Furthermore, some calculations suggest that the energy required to create a warp bubble for a modest-sized spaceship would be equivalent to the mass of the entire planet Jupiter. There are also unresolved quantum mechanical paradoxes, such as the possibility of the warp bubble gathering highly energetic cosmic rays during its journey and releasing them as a devastating blast of radiation upon arrival at its destination. Despite these immense scientific and physical hurdles, these theoretical concepts represent the peak of human ambition. We are a young, planetary species that has barely left its own atmosphere. Yet we are already writing down the mathematical equations required to warp the fabric of the universe. From the quiet, lonely path of Voyager 1 to the grand cosmic mathematics of the Alcubierre warp drive, our technological efforts are a testament to our refusal to be trapped by the physical limits of our biology, driving us to keep reaching out across the cold, silent light years to touch the stars. Our journey through the mind-breaking scale of the cosmic ocean has taken us from the tiny local fraction of a light second separating the Earth and the Moon, all the way to the gargantuan 93 billion light-year boundary of the observable universe. We have watched our fastest speeds crumble into a slow crawl when measured against the silent interstellar voids, the immense spiral arms of the Milky Way, the warped heart of the galactic centre, the grand skeletal structure of the cosmic web, and the chilling, empty darkness of the Boötes Void. The universe has built physical, unbreakable walls of time delay and relativistic limits, separating us from the stars and keeping us anchored to our local scale of existence. Yet, this journey reveals a beautiful, deeply inspiring truth about who we are. Our physical bodies are small, fragile, and bound to a microscopic speck of dust, floating in a silent, endless dark. But we are not truly trapped. Through the power of mathematics, physics, and scientific curiosity, we have built tools to measure the unmeasurable. We have traced the pathways of ancient, warped photons to reconstruct the history of the cosmos, translating the silent broadcasts of the universe into a grand story of our own origins. The light year is indeed a distance that shatters our brains, but our ability to calculate, understand, and appreciate its staggering vastness is the ultimate proof of the boundless power of the human mind.